Hello everyone, myself Chandan, working in Tumpur University, and in here I'm solving a few problems on convergence of a sequences. And in my previous two lectures, I have solved a few more problems on this convergence of a sequences. I'm continuing this. I have solved a few examples, a few problems on convergence of a sequences. So starting with this, to prove convergence of any sequence or any problems to solve or generally to say convergence of a sequence, we have two main important tools. Two main important tools. Two main important tools to check sequence, to check convergence of a sequence. Convergence of any sequence. Any sequence. First is, if you know nth term, if you know or if we know nth term, if we know nth term, then we can directly take limit of that nth term as n tending to infinity. If it is some finite value, then it is convergent. If it is some infinite value, then it is divergent. And if it is oscillates between two values, which implies oscillatory. Another main important tool is, if any sequence is monotonically increasing and bounded above, is always convergent. And if any, this is sequence, if any sequence is monotonically decreasing and bounded below, is also convergent. So these are main important tools to check convergence of a sequence. So if you know nth term, we can directly apply limit of n as n tends to infinity. If you didn't know limit of nth term, then you can use this tool. That is, if a sequence is monotonically increasing and bounded above, then that sequence is always convergent. So in my previous two lectures, I have used these results. To check for convergence, I have used monotonically increasing and bounded above conditions. So in those two, sorry, what it is, if we know nth term, then okay, in these two tools, which one is better to check convergence of the sequence 0.3, 0.33, so on up to point this one. Here we didn't know the nth term. Generally they have given a sequence. If we find out nth term, then it will be more easier to check convergence of the sequence. So because if you just substitute the limit of n as n tends to infinity, we will obtain the nature of this sequence. So or can we convert this to, or can we write it as in the form of a general representation or general form, like if a sequence is 1 square plus 2 square plus 1 up to n square, then the general term is nothing but n square. So we can directly substitute limit of n square as n tends to infinity. We will obtain the nature of that sequence. So can we convert this sequence in the form of a general term, that is in the form of nth term? We can use the condition also, bounded as well as monotonic increasing. Type 1 or okay, so type 1, first type. Okay, it may be confusing. Just I'm solving this. So I'm now in the first type. I'm converting this to nth term. I'm I'm checking. I'm finding out the nth term. If I find out the nth term, then it will be more easier that if you just substitute limit of n as n tends to infinity, we will obtain the nature of the sequence. So I'm just finding out the nth term of the sequence. So this given sequence is 0 0.3, 0 0.333, sorry 0 0.33, 0 0.33, 0 0.333, so on. 0.3 is nothing but 3 by 10. 3 by 10 is nothing but 0.3. 0.33 is nothing but 3 by 100. 33 by 100. 33 by 100. And 0.333 is nothing but 333 divided by 1000. So on. 33.3. Okay. 0.33 is nothing but 33 is nothing but 0.33 is nothing but 33 by 100. So take 3 as a common. We left out with 1 by 10, 11 by 100, and 111 divided by 1000, so on. 3 into multiply and divide by 9. 9 by 10, 99 by 100, 999 divided by 1000, so on. 3 by 9 into 9 by 10 is nothing but we can write it as 10 minus 1 divided by 10. This is 100 minus 1 divided by 100. 1000 minus 1 divided by 1000. Split this term. We left out with 1 minus 1 by 10. 1 minus 1 by 100. 1 minus 1 by 1000. So on. So, general term of this sequence is first term is 1 minus 1 by 10, second term is 1 minus 1 by 100, 1 minus 1 by 1000, so on. Can we write it as 1 minus 1 by 10 power n? This is the general term. Like, suppose they given 1, 4, 9, so on. We can write this sequence as n square. Because if we substitute n is equal to 1, we will obtain first term. If we substitute n is equal to 2, we will obtain second term, that is 4. If we substitute n is equal to 3, we will obtain third term. Like on the similar way, we can write this as in the form of 1 minus 1 by 10 power n. So, general term is nothing but 3 by 9 into 1 minus 1 by 10 power n. So how to check convergence of this sequence is nothing but if we directly substitute limit of this n square as n tending to infinity. So here if we substitute n is equal to 1, n is equal to 1 in this term 1 minus 3 by 9 into 1 minus 1 by 10. So we will obtain 0.3. If we substitute n is equal to 2, 3 by 9 into 1 minus 1 by 10 square, we will obtain this 0.33. So we are converting this sequence in the form of a general term, general representation. Or we can find out this nth term. Therefore, this is nothing but Sn is nothing but, or if we take this sequence as in the form of an, sequence an is in the form of 3 by 10 into So 3 by 9 into 1 minus 1 by 10 power n. 3 by 9 into 1 minus 1 by 10 power n. 3 by 9 into 1 minus 1 by 10 power n. This is a general representation of this sequence, 0.3, 0.33 and so on. There are any questions of like this form, suppose 0.1, 0.22, 0.222, point so on, we can convert this like this so that we can find out this nth term. So what happens if limit of an as n tends to infinity? Limit of an as n tends to infinity is nothing but limit of 3 by 9 as n tends to infinity into 1 minus 1 by 10 power n. This is nothing but 3 by 9 into 3 by 9 into 1 minus limit of 1 by 10 power n as n tends to infinity. This is nothing but 3 by 9 into 1 minus 10 power infinity is nothing but infinity, 1 by infinity is nothing but 0. So we will obtain 1 by 3. So this sequence converges to 1 by 3. 1 by yes, 1 by 3. 1 by 3 is nothing but 0.33 something. Okay. Therefore, this limit of an is finite. This limit value is finite. Limit value is finite. Limit value is finite. Hence, the given sequence. Hence, the given sequence is convergent. This is one easiest method to check convergence of a sequence is in the form of like this 0.3, 0.33 so on. Suppose we can use bounded as well as monotonically increasing condition also. If you check for monotonically increasing, an plus 1 is nothing but 0.333333. An is nothing but one term is lesser. This is nothing but an. See, the sequence is in the form of zero point 0.3, next term is 0.333, next term is 0.333. 3 is added to every term. For previous term, if you add 3, then we will obtain the next term. So like this is an plus 1. How many 3's are there? Something like so on up to, we can write it as something like so on up to n plus 1. Because if we substitute n is equal to 1, we will have just 0.3. If we substitute n is equal to 2, we will up to second term. So an is something like 0.3 so on up to n. Therefore, an plus 1 minus an is nothing but we will obtain something like 0.000003. Whatever this value is greater than 0, therefore it is increasing. It is monotonical increasing. And in fact, every term is in the form of 0.33333 so on. It never exceeds 0.4. Right? Every term in the form of 0.333 means it never exceeds 0.4. Therefore, every term in a sequence is less than 0.4 for all n belongs to n, which implies this sequence is bounded above. Monotonical increasing as well as bounded above. Therefore, this sequence is convergent. This is also, we can use this tool also to check convergence of a sequence. So I am using both the main important tools to check convergence of a sequence. But I think this first method is easier, right? Just we are converting this sequence, general sequence, to we are finding out the nth term. So in nth term, if you just substitute the limit of that nth term as n tends to infinity, we will obtain this limit value which is finite, therefore the given sequence is convergent. And you can use this step also, monotonically increasing as well as bounded above. Okay, now I move on to the next problem. Show that the sequence an where I think it's not visible properly, so just wait, I'm using another color. So the sequence an where an is equal to 1 plus 1 by 2 factorial plus 1 by 3 factorial plus so on up to 1 by n factorial is convergent. So for this sequence, it's a bit difficult to finding out the or this is nothing but nth term. They have given this is nothing but nth term. It's difficult to check limit of this nth term as n tends to infinity, or we can't express what value it converges to what values. Therefore, it's better if you use monotonical increasing as well as boundedness condition. So first sequence where an is nothing but this is convergent. So firstly, I am checking out the monotonically increasing condition. An is like this. An is nothing but 1 plus 1 by 2 factorial plus so on up to 1 by n factorial. So an plus 1 is nothing but 1 plus 1 by 2 factorial plus so on plus 1 by n factorial plus 1 by n plus 1 factorial. Therefore, an plus 1 minus an. This term minus this term is every term get cancels. We will left out with only this term. Therefore, 1 by n plus 1 factorial. And this is always greater than 0 for all n belongs. This is a natural number. First value is 1 by 2 factorial always greater than 0, 1 by 3 factorial always greater than 0. This term is always greater than 0 for all n belongs to n, which implies the given sequence an is monotonically increasing. Monotonically increasing. An is monotonically increasing. An is monotonically increasing. Now I am checking about the bounded above condition. Given an is 1 is nothing but 1 by 1 factorial, 1 by 2 factorial plus so on plus 1 by n factorial. Call this as some equation 1. 1 by 2 factorial is nothing but 1 by 2, and 1 by 3 factorial is nothing but 1 by 6 is always less than 1 by 4 is nothing but 1 by 2 square. We can consider like this 1 by 6 consider me it is always 1 by 6. 1 by 6 is always less than 1 by 4, and 1 by 4 factorial is nothing but 1 by 24 is always less than 1 by 8. 1 by 8 is nothing but 1 by 2 cube. So in a similar way 1 by 5 factorial nothing but 20 60 120. 1 by 120 is always less than 1 by 16. 1 by 16 is nothing but 1 by 2 for 4. So I am using this inequality. By using this inequality, 1 implies 1 is nothing but an is equal to 1 by 1 factorial plus 1 by 2 factorial plus so on plus 1 by n factorial. So I am writing this as the same 1 by 1 factorial, or 1 by 1 factorial is nothing but 1 1 factor nothing but 1, 1 by 2 factor nothing but 1 by 2, and this term is less than, this term is less than, this term is 1 by 3 factorial. This term is less than 1 by 2 square, and next term is less than 1 by 2 cube, plus so on, plus for first term we will obtain 2 power 1. For this third term we will obtain 1 by 2. First term is 1, this term is 1 by 2 power 1. For third term we will obtain 2 square. For fourth term we will obtain cube. So one value is less. Therefore for nth term we will obtain 1 by 2 power n minus 1. Right? First term is same. For second term, this is second term. Here we have how many terms? There are n terms. For second term we will obtain 1 by 2 power 1. This is for second term. So 2 power 1. So 2 square. Okay, whatever the value here, we will get the same value. 1 by 3. So 1 up to n factorial. And therefore this is third term. Third term is less by 1. Less by 1. Fourth term is less by 3. Therefore so on up to 1 by 2 power n minus 1. 1. Okay, this power is 1. This power is third term we will obtain 3. Okay, for nth term we will obtain 1 by 2 power n minus 1, because see here, first term is 1 by 1. This is nothing but 1 by 2 power 0, right? This is nothing but 1 by 2 power 0, 1 by 2 power 1, 1 by 2 square, so on up to here. If it is first term, we will obtain less by 1, 1 minus 1, 0. For second term, 2 minus 1, 1. For third term, we will obtain 3 minus 1, 2. For fourth term, we will obtain 4 minus 1, 3. For n term, we will obtain n minus 1. Therefore, this is nothing but, or this is equal to, this is nothing but 1 plus 1 by 2 plus 1 by 2 square plus 1 by 2 cube plus so on plus 1 by 2 power n minus 1. This is nothing but this thing. But whole term is less than, but this term is equal to this term. This is same as this term. Therefore, this is nothing but geometric series with common ratio 1 by 2. Sum up to nth term in a geometric series. Here there are how many terms? There are n terms. Therefore, sum of n terms in a geometric series in GP, or a geometric series, geometric progression in a geometric in GP. Okay, sorry. N terms in a GP. So, the formula to find out sum of n terms in a GP is nothing but, this sum is nothing but with common ratio 1 by 2. This sum is nothing but 1 minus r power n divided by 1 minus r. Here first term a into 1 minus r power n divided by 1 minus r. This a value is 1. Common ratio is 1 by 2. 1 minus 1 by 2 whole power n divided by 1 minus 1 by 2. So we will obtain 2 into 1 minus 1 power n is nothing but 1 by 2 power n. This sum value is nothing but this. If we substitute n is equal to 1, we will obtain 1 minus 1 by 2, 1 first term. If we substitute n is equal to 2, we will obtain 1 plus 1 by 2 is nothing but 3 by 2. If we substitute n is equal to 2, we will obtain second term. Second term is nothing but sum of first two terms. Third term is nothing but sum of first three terms. Therefore, this is nothing but this general representation of this sequence. Therefore, an is less than, here the inequality is less than an is less than this term. An is less than this term. This term is nothing but general representation of this term is general representation of this term is an is less than 2 into an is less than multiply this term, therefore we left out with 2 minus 1 by 2 power n minus 1. This is nothing but an is less than 2 for all n belongs to n, because this is some positive quantity. This is some positive quantity. Therefore, 1 by 2 power n minus 1 is always less than 1. Is always less than 1, because if you substitute n is equal to 1, we will obtain 1. If you substitute n is equal to 2, we will obtain 1 by 2, which is always less than 1. Therefore, maybe less than or equal to 1, but this is always greater than 0, because n is a natural number. Therefore, this is always greater than 0. Therefore, this value lies between 0 to 1. If you subtract this value from 2, 2 minus the value lies between 0 to 1, we will left out with always less than 2. Therefore, 2 minus the value lies between 0 to 1. Therefore, this value is always less than 2. 2 minus some positive quantity which lies between 0 to 1 is always less than 2. Therefore, an less than 2 for all n belongs to n, which implies an is bounded above. An is bounded above. An is monotonically increasing. We have proved that an is monotonically increasing and an is bounded above. Monotonically increasing and an is bounded above, which implies an is convergent. An is convergent. So now I move on to the next problem. Discuss the convergence of the sequence. Discuss the convergence of the sequence x power n. In series, this is nothing but geometric series. Discuss the convergence of the sequence x power n, where x is a real number. What happens if x is any real number? That is nothing but the real number may be greater than 0, less than 0, or may be equal to 0. Therefore, if we check for some 3 to 4 conditions. Firstly, I check for when x is equal to 1. Next, I check for x is equal to minus 1. X is equal to minus 1. And in third case, I check for every value lies between minus 1 to 1. And in fourth condition, I check for x is greater than 1. And in fifth condition, I check for x is less than minus 1. X is less than minus 1, x is greater less than minus 1, x is greater than 1, and x lies between minus 1 to 1, and x is equal to 1, and x is equal to minus 1, so that I cover a very real number. If we check for all these conditions, it's enough that we check for x belongs to any real number. Real number lies between minus infinity to infinity, so I check for minus infinity to open interval minus 1 is included in this, and 1 open at 1, and infinity 1 to infinity is included here, and minus 1 to 1 open interval is included here, and at the boundary x is equal to 1 is included here, and x is equal to minus 1 is included here. X is equal to 0 is included in this term. Therefore, I am checking out in all these 5 cases. What the nature of sequences in all these five cases? So in first case, x is equal to 1. If x is equal to 1, if x is equal to 1, given sequence an is nothing but x power n. So an is nothing but 1 power n. 1 power n is nothing but 1. Therefore, this is nothing but constant sequence, or you can apply limit. Limit of n as n tends to infinity is equal to limit of 1 as n tends to infinity, which is nothing but 1, which is finite value. Therefore, the given sequence is convergent. The given sequence is convergent. Second case, if x is equal to minus 1. When x is equal to minus 1, an is nothing but x power n is nothing but minus 1 power n. Minus 1 power n is nothing but minus 1 plus 1 minus 1 plus 1. This is nothing but minus 1 if n is odd and 1 if n is even. So clearly it oscillates between these two values, which implies given sequence an is oscillates it oscillates between these are finite values, oscillates finitely between minus 1 and plus 1. It oscillates finitely between minus 1 and plus 1. In third case, it is x lies between minus 1 to plus 1. So, in third case, x lies between minus 1 to plus 1. Therefore, so in subcase A, I check for x is equal to 0. I check for when x is equal to 0, an is nothing but 0 power n is nothing but 0, which is a constant sequence, which is always convergent. In subcase 2, x lies between 0 to 1. When x lies between 0 to 1, which is always positive quantity and denominator quantity is greater than the numerator. Therefore, it is something is in the form of, we can take this term something like 1 by 2. Therefore, an is in the form of 1 by, this denominator quantity is greater. It nature is the same as like 1 by 2, 1 by 3, like that. 1 by 2 whole power n. This is nothing but 1 by 2 power n. I'm just taking some particular examples. But if between 0 to 1, always denominator quantity is greater than the numerator. Therefore, denominator approaches to infinity faster than the numerator. Therefore, if numerator quantity is finite, the denominator quantity always tends to infinity. Therefore, 1 by infinity is nothing but that is always converges to 0. Denominator quantity approaches to infinity faster than the numerator. Therefore, this limit of an as n tends to infinity is nothing but limit of 1 by 2 power n as n tends to infinity is nothing but 0. The behavior is same. 1 by 2, 1 by 3, we can take as a particular examples, and every term lies between 0 to 1 behaves the same as behaving like 1 by 2. When x lies between minus 1 to 0, we can, this is the form of something like minus 1 by 2. Here denominator quantity is also greater than the numerator, but with negative values. It is in the form of like an. An is nothing but minus 1 by 2 whole power n, minus 1 by 2 whole power n. So I'm writing the terms in a sequence, and it is something 1 by 2, 1 by 4, minus 1 by 8, so root 3 we will apply minus 1 by 8, 1 by 16, minus 1 by 32, so on. See the sequence, we can write it as minus 1 by 2 power n if n is odd, and 1 by 2 power n if n is even. I return a sequence in the form of two subsequences. If if this sequence is convergent, every these subsequences converges to the same value. Therefore, I am checking whether these subsequences are converges to the same value or not. Therefore, limit of n as n tends to infinity is nothing but limit of minus 1 by 2 power n as n tends to infinity, and limit of 1 by 2 power n as n tends to infinity. This value is nothing but minus 1 by infinity is nothing but 0. 1 by infinity is nothing but 0 if n is odd and if n is even. Both the subsequences convergent and converges to the same value. Therefore, the given sequence is convergent, which implies sequence x power n is convergent. So when x lies between minus 1 to 1, in every cases the sequence is convergent. Therefore, when x lies between minus 1 to 1, the given sequence is convergent. When x is equal to 1, the given sequence is convergent. When x is equal to minus 1, the sequence oscillates finite between minus 1 to plus 1. So now I am checking about when x is greater than 1. I think that is the fourth case. Okay, in fourth case, we will have, in case 4, when x is greater than 1. When x is greater than 1, numerator quantity is greater than the denominator. Numerator quantity is greater than the denominator. Therefore, numerator approaches to infinity. When the term tends to infinity, numerator quantity approaches to infinity faster than the denominator. Therefore, I take examples like x is in the form of something like 2. The behavior is same. X is something in the form of 2. Therefore, limit of this xn an is nothing but something like 2 power n. Limit of an as n tends to infinity is nothing but limit of 2 power n as n tends to infinity. This is nothing but infinity. When x is greater than 1, the meaning is numerator quantity is greater than the denominator. Therefore, numerator quantity approaches faster to infinity than the denominator. Therefore, this value is infinity, which implies sequence x power n is divergent when x is greater than 1. When x is greater than 1, the sequence is divergent. So in last case, we will have x is less than minus 1. When x is less than minus 1, x is in the form of something like minus 2. Minus 2. Therefore, an is nothing but minus 2 whole power n. So this is just write this in the form of sequence terms. We will have minus 2, 4, minus 8, 16, that's 2 power 4, 16, minus 32, so on. Minus 2 square is 4, minus 2 cube 8. Okay. Then we will have this can be written as in the form of subsequences minus of 2 power n if n is odd, and 2 power n if n is even. If this sequence is convergent, finding out the subsequences limits. Therefore, limit of an as n tends to infinity is nothing but limit of minus of 2 power n as n tends to infinity. This value is nothing but minus into 2 power infinity is infinity. Therefore, this is nothing but minus infinity. This is nothing but minus infinity if n is odd. And this limit of as n tends to infinity 2 power n, this is nothing but infinity if n is even. Therefore, this sequence oscillates between these two values. These are nothing but infinite values, which implies sequence an is nothing but x power n oscillates infinitely. It is not finitely oscillating. It is nothing but infinite. Both the subsequences are not. Both subsequences are not. We are not getting finite values in both the subsequences. Therefore, there is not infinity. One is minus infinity. One is plus infinity. Therefore, oscillates infinitely. Which implies we can say an is oscillatory. an is oscillatory. If you write it in the form of a series form, the nature is same, but the representation is different. Series is nothing but sum of these terms in a sequence. Therefore, in first case 1, case 2, case 3, case 4, case 5. In case 1, x is equal to 1, the given sequence is convergent. If x is equal to minus 1, the given sequence is oscillates finitely. In third case, when x lies between minus 1 to 1, when x lies between minus 1 to plus 1, the given sequence is convergent. Of course, this is converges to 0 itself. When x is greater than 1, the given sequence is divergent. When x is less than minus 1, the given sequence is oscillates infinitely. Therefore, to ask any questions in examinations, suppose that we discuss the nature of this sequence x power n, we just check out these 5 cases. Therefore, we are checking out for every real number. This represents a very real number. Therefore, when x is equal to 1, the sequence is convergent. X is equal to 1, x is equal to minus 1, and x lies between minus 1 to plus 1, x is greater than 1, x is less than minus 1. Therefore, we have considered every real number. And in every cases, the behavior is different. oscillates finitely when x lies between minus 1 to 1, it is converges to 0, whatever this is convergent. When x lies between, here there are three sub cases. In third case, I have discussed 3 to 4 sub cases, but in single cases we can explain the convergence of a sequence, because in every case the sequence is convergent. In fourth case, we can take like that, because when x is greater than 1, this is simpler, like numerator quantity is greater than the denominator. If you take any sequence, the nature is similar to this sequence, therefore I taken 2 power n, something like 2. Therefore these are the results. If you have any doubts regarding any problems in my videos, you can comment on the comment box. Okay, thank you. Thank you so much. Thanks for watching.